All right, welcome. Likely you saw the introduction to the Matrix of Time series, and you were intrigued enough to jump in and learn some interesting insights into time. So let's start. So time, how well do we understand it? Let's start with the common understanding of now. So we have a person who's in the present, and we'll put that as a point in time called the now. And now when we add the past, we typically put it behind us and we draw a line. We represent it as a line from the past to the now, going on into the future. So we think of time as a pseudo one-dimensional line. But when we think about time in reality, we find time in the smallest part of the atom. In the largest part of the universe, time is there and is also inside of us. Clearly, we age according to some universal clock. And so time as a 1D variable cannot be everywhere. So time as a line is not quite accurate, but it's certainly easier to visualize. And later on, we'll investigate a better way to think about time and to represent time. So, what is time? Here is a representation of time. It looks invisible and it looks undetectable, and that's pretty much the way it is. But what happens if, on the tiny scale, we introduce just one atom? And soon afterwards, the atom emits light. We've witnessed a change in matter, and now we need a technique to measure this change at the atomic scale. What about the larger scale? Let's introduce a planet, and the planet rotates a quarter of a turn. Again, we've witnessed a change in matter, and we now need a technique to measure this change. How do we measure change? You might say, that's how I measure change. I have a clock on the wall, I see the passage of time, and I can tell the difference between 9:20 and 10:20 and 3:30. And that's how I measure it. But what is it that we're actually measuring? Let's look at a little diagram of our solar system. We have the sun in the center, we have the earth spinning around the sun, and we have the earth spinning around its axis, and we have the moon and the stars. So when the earth spins around its axis, we call that a day. So a day is defined as the change in the earth's surface relative to the sun and the stars. All right, so we've defined a day. But what about the earth's rotation around the sun? Well, we all know that we define that as a year. So again, this is change in the Earth's location is being used to define our time. And so when we look at this, our day can be considered clock time, and the year can be considered calendar time. And the clock is just a more useful way to break down the change in the rotation of the Earth as it goes around its axis into more useful units of hours, minutes, and seconds. But we shouldn't get the two confused. The last couple of slides should have made it clear that what we are doing with our watches, our smartphones, and the clocks on the wall is we are measuring change and we're calling it time. Think of it this way. We use the units of Celsius and Fahrenheit to measure temperature, to measure heat. But you would never get confused and say that Fahrenheit is heat. It's a measurement of the amount of heat that's in a system. And the same here, that time is a measurement of the amount of change in a system that it's linked to. So hopefully you get a better understanding of the separation. So the real fundamental process that is beyond clock time and calendar time is change. So what also should be clear from the previous slides is that without matter in the universe, time, the matrix of time, is invisible and undetectable. It's only because there is matter in the universe that it is possible that we can actually measure change and then have units of time to measure the passage of time. And this is what we commonly refer to when we have that pseudo 1D line. We're looking at the passage of time. And this is also true for space, the matrix of space. If you take out matter, there is no possible way to determine what space is, and it is undetectable. And that's a bit of a strange thing, because typically we think of space, we look outside and we see houses and trees and buildings and roads and cars, and we say, I can see space. But what you're actually seeing is you're seeing matter inside of space, and you're measuring space relative from one piece of matter to another. So hopefully that gives you a different perspective. It's sometimes a little bit unnerving to think that the most fundamental property of our universe, space and time, is invisible and undetectable, and that it requires matter to give it any structure at all. But hopefully that's become clear to you in these last few slides. So we live in a universe that is in constant motion, from the smallest parts of the atom to the largest parts of the cosmos. There is motion. And so it's really important that we understand what is motion. Let's look at the definition of motion. Motion is change in location in space divided by change in clock time. So that could be also thought of in terms of the amount of distance divided by duration. Those that have a technical background will be familiar with dx dt. If we take time out of motion, we're only left with location. So there's no possibility of changing that location. So everything in the universe stops moving, and the universe cannot change. So again, we come back and we see that we have change linked to time. Even our clock time and calendar time stop working if we take out the denominator. It's not possible to see how in the universe there has to be motion to generate change, and it is in motion that this change is linked to time. Now we'll talk about the direction of time. The equations in physics do not limit time to only going forward. In this diagram, we show a poor human who is constantly running because they feel like they're behind time, and at some point in the future they look forward to a time when they can actually relax and not be chasing them all the time. But physics says it doesn't always have to go in this direction. It can also go in the backwards direction. And here we have a human that's running from the now into the past. So what is it about a universe that has science telling us that time can only go forward? So physics states that the direction of the universe is from order to disorder, known as an increase in entropy. And there are two examples that we can give. One is here we have a mirror, and it cracks. We never find that the mirror will then repair itself without any outside interference. Basically what we have to do is we have to throw away the old parts and cut a new mirror. The second example is an egg. So we have an egg, the egg cracks, and there's no way to put the egg back together again. So we started with order, which is a complete egg. It went to disorder. We had a cracked egg, and all the innards fell out, along with the yolk and everything else. And there's no way to put this egg back together again. So there's no way to go from disorder to order. So because of this, physics has said that there is basically a flow of time that goes from order to disorder, and we call this time going forward. But is it really that simple? Let's look at two examples that challenge this idea of time only going forward. The first example is a time reverse mirror. It's also known as an optical phase conjugate mirror, which is quite a mouthful. The second one, in another video of this series, will discuss the implication of the quantum eraser experiment to the direction of time. And in these two cases, we'll actually see, in the first example, we'll see that there's an opportunity to go from disorder back to order. So while our experience is almost universally that time goes in one direction, there are examples where it can be reversed. And so let's talk about these next. All right, let's look at an ordinary mirror. In here I have an image on the left-hand side of a zebra, and we're going to take that image and the light from it is going to go through a distorted piece of glass. Think of something like the door on a shower, and the light waves get distorted, and on the right-hand side we see an image of what the zebra looks like when it goes through this distorted piece of glass. Now, if we land up taking this image and we reflect it through an ordinary mirror, it goes back through the same distorted glass, and it comes out twice as distorted. So you can see it represented in the bottom left-hand side here, and it's barely recognizable. In fact, if you didn't know that the image started out as an image of a zebra, it would be very difficult to even determine what this image down on the bottom left is. The time reverse mirror. So we have the same setup as before. We have the zebra image on the left, and the waves go through the distorted glass, and then they are distorted, and we see that in the right-hand side image here. Now, when we put this mirror, this time reverse mirror, we notice that the distorted wavefronts are what they call conjugates of each other. In other words, they are reversed in time. So basically, the last part of the wave going into the mirror is the first one out, and the first part of the wave is the last one out. So it goes back through the distorted glass, and the distortion, because it's time reversed, lands up undistorting itself, and the restored image comes out the other side. And what I'm going to do in the next two slides is explain how this is possible by looking at what happens with an ordinary mirror and with a time reverse mirror, because it's interesting to understand exactly how something like this could happen. So let's go back to ordinary mirrors, and I want to introduce the concept of phase and how phase represents the distortion. So on the left-hand side we have the familiar zebra image, and we're going to represent that by these 6 marchers that are marching across this football field. And in the middle there is a distortion, and one of the marchers, because this is in their way, has to go up the steps, across the platform, down the other side. And while this is happening, the other marchers are continuing on at the same rate. And on the other side, you notice that this particular marcher is behind because they've had more distance to go. They had to go up the steps, across the platform, and down the steps. And this set them out of phase with the rest of the marchers. Now, as these marchers approach, well, let's assume that there is this mirror and it has an ordinary mirror properties. So when they reflect, what happens is that the marchers that are in the lead continue to be in the lead, and the marcher that's lagging continues to lag. Now, the white representation is the reflection. So as they go across again, this poor marcher that now has this distortion in the center here has to walk up and walk down, and so now they are further behind, and so the distortion looks, as we can see here, even worse. And so you can imagine that all the little imperfections in the distorted glass are represented by these types of steps, and each one would then create a phase delay of the particular point on the wavefront represented by these marchers, and you get on the back side here something that's far from a straight line. It's completely distorted and is represented by the bottom left-hand image right here. Okay, so now let's apply the same format to the time reverse mirror. And we have exactly the same format. The marchers marching across the field, all in line. The middle guy hits the distortion and has to walk up and down, and he has a phase delay. But now, what happens when we hit the time reverse mirror? You noticed that there is a inverse reflection here. And what happens is the guy that came in last is now first, and the group that came in first are now last. And this is what is known as a conjugate mirror. And a conjugate in some ways is opposite or inverse. And with regards to this mirror, conjugate means that the first in are the last out and the last out are the first in. So what happens now is as these guys march down the field, this middle guy has to go back up the steps across the platform, back down to the other side. And since everybody's marching at exactly the same speed, that puts him exactly back in line, and everybody is now in sync again, and we get the complete image out the back side right here. And so these time reverse mirrors, they can be recorded in an emulsion film, but the more commonly they're recorded in a tiny crystal called a photorefractive crystal, and it creates what is known as a holographic mirror that has time reverse properties. And you can see now when we look at, when you call this by its real name, optical phase conjugate mirror, you can see that the phase is introduced by the distortion. The conjugate is this first in, first out. First in, sorry, last out, first in. And so this particular holographic mirror will create this. And what's interesting is you could actually change this image, and what will happen is that the reflected image below it will look all garbled, because it takes, depending on the type of crystal that you have, there's a certain time response, but it could take up to a number of seconds, and the hologram will rewrite itself in such a way that it does the perfect conjugate reflection, and then the image will slowly reconstruct itself, the reflected image, so that it matches the input image. So it's very interesting. In fact, holographic mirrors have all sorts of interesting properties. One of the other properties that is pretty neat is that if you have a reflected a light beam, say a laser beam that goes into a holographic mirror, it'll be reflected along exactly the same path that it came from. So the reflected light goes back into the light source, where if you had an ordinary mirror and you shone a light at, say, 30 degrees from the face of the mirror, the reflected beam would then reflect to the other side 30 degrees away from you. And so there are some unusual aspects to this, but the time reverse certainly shows you that is one example where time can be reversed. And in some ways, we talked about the property of entropy, where things go from order to disorder. And here you can see that a holographic mirror actually takes the disorder and restores it and brings it back to order again. Takeaway messages. All right. From this series, we've taken away the following concepts: that time is invisible and not detectable. It's matter in time that makes it detectable and gives time the structure that we relate to. What we call time is a measurement of a unit of change. It'll be called clock time. For the year, it'll be called calendar time. More fundamentally, it is an agent of change in our universe. In the second part of this series, we'll be talking about the following. We'll look at the space matrix. And what do we know about matter? Without it, we have no sense of space and no sense of time, so it really matters, no pun intended. We'll look at how matter can be represented in two very different ways. And we'll touch lightly on the idea that what we see is all relative. If you'd like to watch more of the Matrix of Time videos, please hit the subscribe button and you'll be notified of new presentations. You can also visit my webpage at www.multidimensionaltime.com, and in there you will see a reference to a book I've written that you might be interested in. Also, I have a page with technical papers. There's an intro paper, and there is a paper called Three-Dimensional Time and Consciousness in the technical section that'd be of interest to people with and without a technical background. And then the rest of the papers require an engineering or science background because they get quite technical. So again, please hit subscribe and join me in not only future videos of this Matrix of Time. There will also be other series related to space and time that I'll be doing in the future, and you'll at least be notified of those as well. Okay, thank you very much.